Hello! In this work, we present a particle-based COVID-19 simulator with contact tracing and testing modules. In this work, we have developed a particle-based simulator which models each individual as a unique particle with parameters such as location, velocity, epidemic state, time for being at current state, availability of the contact tracing application, and testing result. The particles move on a 2D map representing a certain area as shown on the box on the right, and get infected if they come to infectious particle closest in a predefined physical distance or contact threshold in our context. The position of the particle changes after each iteration based on the velocity, which is constantly updated as well. The contact tracing module is based on the use of a mobile app, and it stores the list of contacts for each particle such that if the particle is determined to be infected, then all particles from the list are quarantined or isolated. The testing module simulates the massive random testing of the population. The module considers test sensitivity and specificity. This way, the simulator is able to simulate different scenarios and mitigation policies. So here is the state chart of the model. We have 4 superstates: susceptible, exposed, infected, and recovered. Exposed superstate consists of exposed and quarantined states, and where quarantined state consists of 2 substates, true quarantined and false quarantined. The infected superstate consists in turn from infected, isolated, and severe infected states, an isolated state composed from true and false isolated substates. Initially, all particles are susceptible. Once some of the particles come close to contagious particle, they become exposed, and after the exposure period, the particles transition to the infected state. In the infected state, some of the particles become severe infected depending on the SIR parameter, and the rest go to recovered state after the infection period is over. As for severe infected particles, depending on the gamma mortality rate, they transition to dead and recovered states. For this particle-based simulator, we added a testing module that integrates testing parameters such as test specificity and test sensitivity. We are testing susceptible, exposed, and infected particles, as we don't need to test quarantined, isolated, or severe infected particles. Susceptible particles that were tested false positive by the test are sent to false isolated state. As they are not infected, they will go back to susceptible state after the infection period is over. Exposed particles that are tested positive stay in true quarantine substate until the exposure period is over and then transition to true isolated substate. In this substate, some of the particles transition to severe infected state and the rest become recovered after the infection period. As for the particles that are infected and tested positively, they go to true isolated state. And secondly, contact tracing module is implemented. Contact tracing checks contacts of the previously positively tested particles. If contacts of the positively tested particles are exposed, then they are sent to true quarantined substate. And if contacts are infected, then they are sent to true isolated substate. Contacts of the particles that were previously identified false positive and were sent to false isolated substate go to false quarantined, and after the exposure period, they become susceptible again. To conduct further analysis and parametric simulations to test particle-based simulator, we have chosen the province of Lecco in Lombardy region that was the epicenter of the COVID-19 outbreak in Italy. Based on the recent seroprevalence survey conducted by the Italian Ministry of Health, the number of people encountered the infection is approximately 6 times larger than the officially published statistics. So, using the timeline of governmental policies such as quarantine, different restrictions, and lockdown in the region, we have performed the validation scenario for the province of Lecco. The table on the left shows respective parameters that were used to imitate different policies. As we can see from the figures, the particle-based simulator is accurate. The peak of the infection have been accurately identified by the simulator from mid-March till mid-April. Further, total cases is 5 times larger than the officially registered cases, which is in accordance with seroprevalence tests result. And the total number of deaths is close to actual data. To illustrate the effectiveness of each of these 2 modules, we have performed a parametric analysis that is provided in the paper. But for now, let's have a look on the 3 different following scenarios performed on the previously calibrated model for Lecco province in Italy. Scenario 1. No contact tracing and testing modules are used. Scenario 2. No contact tracing and 20 tests per 1,000 people. And scenario 3. Contact tracing is set to 1 and 20 deaths per 1,000 people maintained. So here we can visually observe how does the infection spread for these three different cases go. For the first case, when no contact tracing and testing is used, we can see that the epidemic grows much faster and starts spreading from different locations. Integration of the testing in the second scenario allows to localize and slow down the epidemic spread, and in the third case, it slowed down much faster. As we can see, the area of infection spread is much larger in the first case compared to second and third. So, at the peak of the infection period, the number of infected reaches 4,925 in the first scenario, 1,841 and 1,004 in the second and third scenarios respectively. Further, with the implementation of different restrictions and lockdowns, the epidemic is suppressed in all three cases. But after restrictions are lifted up, we observe sudden second wave in the first scenario, smaller rate of infection spread in the second scenario, and in the third one it's almost completely stopped and controlled due to total contact tracing of the population. From the results of these simulations, we observed that testing enables to decrease the number of deaths by a factor of 2, from 630 in the first scenario to 294 in the second one. And addition of the contact tracing resulted in 177 deaths, which differs a lot from other two cases. So, from this analysis, we can see the effectiveness of each tool in suppressing the viral infection spread. Testing is a good tool, but cannot be as effective as contact tracing in avoiding the second wave, suppressing the infection spread, and controlling further epidemic state in region.